Our next unit will be application. This will be our final calculus unit before moving on to vectors. Before we get into applications, however, let's take a moment to add two more techniques to our repertoire. The first technique we're going to look at is implicit differentiation. Before we get into this, let's take a moment to recall the chain rule. When I defined it previously, I did so using Newton's notation. I defined it as the derivative of f of g of x is equal to f prime of x evaluated at g of x times the derivative of g of x. This was useful in many instances. However, when we take a look at implicit differentiation, it will be more useful to look at this using Leibniz notation. So first, let's separate this into two separate functions. If we take it as a function y equals f of u, and then u equals g of x, you notice that this is the same thing as u is the parameter for f, yielding the same thing as f of g of x. We can then redefine our chain rule to be the derivative of y with respect to x will be the derivative of y with respect to u times the derivative of u with respect to x. Let's take a look at an example and see how this would apply. When we're taking implicit differentiation, we're typically doing this in a case where we have a relation or function that is in terms of both x and y. So take a circle, for example. If we wanted to determine the slope of the tangent at the point 3, 4 of this equation, x squared plus y squared equals 25, we can approach it using implicit differentiation. So let's take a look. We would take the derivative of each of these terms as normal, taking the derivative with respect to x. The first term is a function of only x. So when we take the derivative, our result would be as normal, 2x. The second term, however, is a function of y. So our chain rule now tells us that we will take the derivative of y with respect to itself, so 2y, and then multiply it by the derivative of y with respect to x. We now see we end up with an expression for the derivative of y with respect to x in terms of both x and y. We were interested in finding dy by dx, which is the slope of the tangent. Let's rearrange this equation now for dy by dx. Notice here we get dy by dx is equal to minus x over y. This is a function that is in terms of both x and y. We can take the point that we were given both the x and y coordinate, and we can sub it into our equation to find the tangent that we were interested in. The slope of the tangent at 3, 4 will be minus 3 over 4. Well, why was it important for me to specify both the x and y coordinate in this case, when in all previous examples we were given only the x coordinate? Well, if we take a look at the graph, as we already said, that the graph is a circle of radius 5 centered at the origin. If we take a look here, if we were to only specify the x coordinate, because this is a relation and not a function, there are 2 points that have the x coordinate 3. We have the point 3, 4 and the point 3, minus 4. Both of these, however, have different slopes of tangents. This is the reason why we have both x and y needing to be specified in our derivative. Next, let's take a look at another technique. The final technique we're going to add to our calculus repertoire is logarithmic differentiation. This technique will come in handy when we come across functions that don't fit any of the derivative rules we've already defined. If we take a look at the function y equals x to the x, this doesn't fit into any of the rules we've already defined. You might think this fits into the power rule that we already defined in chapter 2. However, it doesn't. In that case, we had x to a constant. In this case, our exponent is a variable. In order to handle this, we can apply techniques that we've already learned in advanced functions to get this into a form in which we're now able to solve. If we apply the natural logarithm to both sides of this equation, we end up with ln y on the left, and applying logarithmic rules, we can end up with x ln x on the right. We can now use implicit differentiation to differentiate this. If we take the derivative of the left-hand side with respect to x, we will again take the derivative of the outer function with respect to y, and end up with 1 over y, and then take the derivative of the inner function, y, and end up with dy by dx. Similar to the first example, we end up with an expression for dy by dx that includes both x and y. Let's simplify and rearrange this expression for dy by dx. Now, it may seem undesirable here to have the derivative specifying both y and x as parameters, so we actually know what y is. We can then replace the function y with what it's equal to in terms of x to the x. And this yields the derivative with respect to x in terms of x only. Next, Let's take a look at an example of a related rates problem. We will see a variety of these types of problems, most of which will be geometric in nature. Well, what is a related rates problem? Typically, these problems will involve a known rate, and we're trying to figure out how the rates that we know involve rates that we don't. So let's take a look at an example. If we're given a problem like this one. Suppose we have a cone-shaped cup. That cup is of dimensions 12, height of 12 and a radius of 6. If water is slowly being poured into the cup at a rate of 9 centimeters per second, we want to determine that how quickly the water level is rising at the point where the depth of the water is 6. Well, how should we approach this problem? We should always start with a diagram. Next, let's identify a piece of information we were given. Well, we were told something about how the volume is changing, 9 centimeters cubed per second. We should recognize this as a change in volume, as 9 centimeters cubed is a measure of volume, and it's a time rate per second. Next, let's also identify, we were asked to figure out how quickly the volume is changing, or the depth of the water is changing, when we're at 6 centimeters deep. The final piece of information that we have is that, that it is in fact a cone-shaped cup. So we can make use of the volume formula that we've known since grade 10. Next, we realize that if we were to apply the techniques that we just learned, implicit differentiation, to differentiate this function, we would in fact end up with a time rate for volume, dv dt, we would end up with a time rate for the radius, dr dt, and the time rate for height, dh dt. Some of these pieces of information we have, some of them we want to find, and some of them are not very useful to us. We know dv dt, so that appearing in our derivative is fine. We want to know dh dt, so again, that piece of information we want there. However, we don't know anything about how the radius is changing at any point. So let's take a look at the geometry here. We knew that the height of the cone was 12 and the radius was 6. We can make use of similar triangles in order to figure out the radius to the height at any given point. So if we have some point h here, we can figure out using similar triangles what the radius will be. If we rearrange this equation, we get that at any point, the radius is going to be half the height. This will be useful to us. If we replace this piece of information in our original equation, notice here that we get an expression for the volume in terms of only h. This is now good. If we take the derivative now, we end up with an expression involving dv dt, h, and dh dt, all of which we know. Thus, rearranging for dh dt, which is what we wanted to find, this representing the rate that the depth of the water is changing, we can then sub in the piece of information that we had, the rate that the volume is changing, as well as our known height. When we sub this all in and simplify, we end up with the rate that the depth is changing at about 1/3 of a centimeter per second. We'll see several more examples of this throughout our homework. Don't forget about your first and second derivative tests. These will also become very useful to you when looking at other forms of problems. Good luck.